Now, in McCabe, you'll be able to see this particular example on determining the number of stages for a distilling column, wherein the operating lines are already drawn. Okay, so this is your enriching section operating line, and this is your stripping section operating line. This is your feed line. The feed tray or the feed plate, if you notice, is the fifth plate, because if you're going to have this enlarged, the transition from the enriching section to the stripping section is really happening on this plate, because the bottom part in here is still on the enriching section, and then the upper part rather, and the bottom part in here is in the stripping section already. So this is your feed tray, not number 4 but number 5, because that's where the transfer of your steps here from one section to another occurred. So the very first occurrence of that. So this is your location for the feed tray. Okay. Now we will have a specific example later and how is it done. Now there are instances. Okay, I'll first continue that way. We covered everything for today. There are instances wherein you are required to determine the minimum number of stages that will affect the separation, or that will achieve the purity of the distillate that is specified in the problem. So that's a condition of total reflux, or that's a condition wherein all the liquid that is from the condensed vapor is returned back into the column. As such, the term total reflux. As a consequence of that, we have what we call as the minimum number of stages. So there's no point anymore of determining the enriching section operating line, the stripping section operating line, nor the location of the feed plate, or drawing the Q line or the feed line. Because in here, you will simply need the X sub D, the mole fraction of your A, let's say benzene in the distillate, and the mole fraction of benzene in the bottom's liquid. That's where you're going to start making your steps until you land straight on X sub W or beyond it. So in this case, class, you have no operating lines anymore. You just simply make these steps here, touching the equilibrium curve from the 45-degree line. I have mentioned also as well that the last plate that you're drawing here, or the last stage that you are making here, is your reboiler. So in this case, this is only like 3-point-something stage, 2-point-something stages, because this is only 3-point-something in terms of number of stages, probably 3.70 or 3.80. Minus 1 for the reboiler, so that would only be like 2.80 or 2.70. This is in a condition we call total reflux, and it's being explained in here. So in the condition of total reflux, all product distillates and bottoms are reduced to 0. Now, why is it reduced to 0? Because all liquid in the bottoms are reboiled. So I miss mentioning this, and returned to the tower as vapor, and all overhead condensed vapor are returned to the tower as reflux. And because I'd like to emphasize on total reflux. So in the condition of total reflux, all condensed liquid is returned into the column as such total reflux, plus all the bottom's liquid, all the liquid that is collected at the bottom of the still is turned into vapor by your reboiler, and all is returned back into your column. Now in this condition, this requires infinite sizes of condenser, reboiler, and tower diameter. So meaning, class, there's no limitation as to what would be the size of your reboiler, what would be the size of your condenser, and also the size of your tower. In short, this will require bigger condensers, bigger reboilers, and of course a bigger tower. Why? Because you're going to return everything back into your column. The term infinite here implies that there shouldn't be any limitation as per design as to the size of the condenser and reboiler that will enable all the condensed liquid to be returned back into the column and all the bottom's liquid to be boiled up as vapor. back also into the column. So this gives the minimum number of trays to be used to obtain the given separation. So this will require less stages, shorter tower, but bigger in size, meaning the diameter of your tower is bigger for the distilling column that is. This is in the condition of total reflux. Now, if we have total reflux and we have determined the number of stages corresponding for it to be the minimum number of stages graphically, there's an analytical way of determining the minimum number of stages or trays. And this equation that you could see here in the slide is given to us by Finsky. It can also be found in your handbook. So a total reflux, total condenser is used. So a total condenser is used, and R here, your reflux ratio is equal to infinity. Okay? So infinity in the sense that you don't have a D. You only have an LO. There's no distillate because everything is returned into the column. If there's no distillate, then R will be 0. Rather, the division in your R, since this is reflux ratio, will be a division by 0. So that is why it's infinity. Now, the minimum number of plates, according to Finsky, could be solved using this equation. You need the mole fraction in the distillate and the mole fraction in the bottom's liquid. Now, you need as well in here the log of the relative volatility of 1 with respect to W. Or this is actually the geometric mean. The geometric mean of the relative volatilities of the overhead vapor 1 and the bottom's liquid W as represented in your handbook. So you take the product of the two and get the square root of the product. That would be the geometric mean of their relative volatility. You take the log of that, and that should be used in here. That's how we determine the minimum number of stages analytically. And we will use this particular equation later for a sample problem wherein we're not already relying on the construction of the operating lines, but we're relying on graphs to determine the number of stages and other information related to the problem that we need to determine. So this is minimum number of trays or stages determined analytically. Now, if we have here the condition of total reflux, we also have a condition of minimum reflux. So the minimum or the least amount of condensed vapor returned back into the column, that's minimum reflux. So the reflux ratio here is that reflux ratio that will require an infinite number of trays. If total reflux gives the minimum number of stages, minimum reflux gives the infinite number of trays. So meaning if you would be asked what's the number of trays at this particular condition of minimum reflux, you cannot answer that. It's infinite. It cannot be accounted. Okay? At minimum reflux. So this corresponds to minimum vapor flow in the tower and minimum condenser and reboiler sizes. So it's actually the exact opposite of the condition of total reflux. There, your condenser and reboiler are big or huge. In here, you have the minimum sizes for the two. Why? Because your vapor flow back into the column is also at its minimum value. Okay? It's also at its minimum value. In here, the operating lines referring to the enriching section and stripping section operating lines moves farther from the 45-degree line and closer to the equilibrium line, which makes the number of steps required infinite. Or if you're going to determine it graphically, it will be impossible for you to count the steps that you have drawn because the two lines that were mentioned, enriching section operating line and stripping section operating lines, already move farther from the 45-degree line. The farthest it is from the 45-degree line and the nearest these lines are on the equilibrium curve, the the more number of stages will you be needing for your separation. Now we go back to our original fundamental discussion. Why do we have more number of stages to effect a given separation at this particular condition of minimum reflux? So as discussed at the beginning, we have mentioned that the farther is your curve from the 45-degree line, the greater the ease in separation. Why? Because if you're going to draw the steps there, you will only have the least number of steps to effect the given separation. But if we have already the operating lines and it will be drawn nearer and nearer to the curve, then you will have more steps to make to effect the same given separation. Now to illustrate what that means, you have this one. So if your enriching section operating line and your stripping section operating line moves farther from the 45-degree line, as a consequence, you'll have more steps to effect the same separation, to have the same XT and XW. The nearer these two lines to the 45-degree line, the least would be the number of these steps. So it's going back to that primary fundamental principle of separation. The farther the line is from the equilibrium curve, the greater the ease in separation. The nearer it is, the more stages you need, meaning hindi siya hapos i-separate. Now, you could see in this particular illustration the pinch point. So this pinch point actually is the intersection of the enriching section operating line on your equilibrium curve. The intersection of your enriching section operating line to your equilibrium curve. Oftentimes, I suggest to my student that you draw first the Q line or the feed line. So this, let's say for example, this is your Q line or your feed line. It's going to intersect your curve at a particular point, which is the same point as the intersection point of the enriching section operating line on the curve. So masunod lang ang enriching section operating line sa intersection point sa Q line sa curve. So this particular point is the pinch point. So first you draw the Q line where it intersects your curve. That would be the same point where your enriching section will intersect it. The same thing with the stripping section operating line. This one has the coordinates x prime and y prime. So we call this as the pinch point coordinates. And these coordinates appear in the formula in determining the minimum reflux. The minimum reflux which brings about the infinite number of stages or trays in your column. Oftentimes, this is the condition of the minimum reflux. Okay? Your feed line touches the curve at that particular point we call the pinch point, and that's the same condition that brings about the infinite number of stages. However, we also have this condition in here before I present to you the formula, wherein we also have this called as the minimum reflux. Excuse me. As you can see here, your Q line touches your curve at this particular point in here. However, this would have been your x prime, y prime, because this is the intersection of the feed line to the curve. However, when you have drawn already your, shall I say, the enriching section operating line starting from the XD, and you try to reach this point where your Q line touches your equilibrium curve, you've noticed that at some point, this enriching section operating line is already tangent to the curve. In our dialect, wala pa di siya nakakross sa point kundi nag-cross si feed line sa equilibrium curve, nag-tangent na siya sa diri nga portion sang curve. In these cases, class, your pinch point is not this anymore, but rather your pinch point would be this point here where your enriching section operating line is already tangent to the curve, not this one. But oftentimes, this is the condition really for minimum reflux. But Sometimes it pays to have it drawn right on the equilibrium curve if you have the data, the XY data pair. That way you can check whether the pinch point coordinates from the intersection of your feed line on the equilibrium curve will not bring about this particular condition for your enriching section operating line. But if the problem does not give you already X and Y, then we have to assume that it would be this particular type of condition, wherein your enriching section operating line does not have any tangential point in your equilibrium curve. Okay? So in here, if you do it graphically, you could see the X prime, Y prime, and it appears here in the formula for the minimum reflux ratio. Okay, so your minimum reflux ratio R sub M divided by R sub M plus 1 is equated to this, wherein you substitute the pinch point coordinates here, X prime and Y prime, together with the mole fraction of the distillate to give the R sub M. There are lots of problems in distillation that requires you at some point to determine the minimum reflux ratio. And this is how you determine the minimum reflux ratio. Okay? We have total reflux. We have minimum number of stages. We have minimum reflux corresponding to infinite number of stages. Now, in terms of economics, we also have what we call optimum reflux ratio. Okay? Optimum reflux ratio. So this is based now on economic balance of the fixed cost of having your tower or your distilling column and the cost incurred in operating it. So considering these two, the value of the optimum reflux ratio as suggested by the handbook is 1.2 to 1.5 or 20 to 50% more than the minimum reflux ratio. That's the optimum reflux ratio. Okay, this is given by the handbook. Now then, if you're going to determine in terms of, let's say, a specific value, what will you answer? Because this one is a range of values, 20 to 50% more of the minimum reflux ratio. We optimize it plus to 1.5. So oftentimes, if you look at sample problems in the book, the optimum reflux ratio is most of the time 50% of the computed, or 50% rather more of the computed minimum reflux. So you can read that on this section of your handbook. Okay, so for this afternoon, I've covered the part which we need so that everything is clear before we go to the first sample problem here that I have placed. So far, in what I have covered, do you have any question in here? Okay, this is where we started. Have that. Have any question here? So no question. Okay, so if there's no question, then we'll go to our sample problem. This will be short because actually this is one of the many quizzes that I have in my test bank, and I chose to have this because in here you will be required to draw the equilibrium curve, and I have it already pictured for you to see how it will look like. So this is a problem actually from Gian Kuplis. Okay, for this problem, you're given a saturated liquid feed of 200 mole per hour at the boiling point. So it's at the boiling point where the bigo. At the boiling point, containing 42 mole percent heptane and 58 mole percent ethylbenzene. And it is to be fractionated at 101.32 kilopascal to give a distillate containing 97 mole percent heptane and a bottoms containing 1.1 mole percent heptane. Now, the reflux ratio for this is 2.5:1. You are required to determine the mole per hour of the distillate, the mole per hour of the bottom's liquid, and the theoretical number of trays for this column, and the feed tray number, or where should the feed be introduced. Now, the equilibrium data for system heptane and ethylbenzene is given here. And along with this data is the temperature. So this is the mole fraction of heptane. So meaning of the two components that we have here, heptane is the more volatile. Oftentimes it's the one that is given, or oftentimes, no, all the time it's the one that is given in terms of concentration to plot on the equilibrium diagram, because we want to monitor how will this particular more volatile component be separated, or how easy will this heptane be separated from ethylbenzene. And you have here the mole fraction of heptane in the liquid phase, and this is the mole fraction of heptane in the vapor phase at this particular temperature. Now, when you're given such a problem wherein it's not the usual benzene toluene system, because sample problems in the book are all benzene and toluene with the exception of some, then you need to plot this one in your Cartesian plane. You will be producing a curve, which is the equilibrium curve for the system here, heptane and ethylbenzene. So I'd like to share my screen to you on the resulting curve for this system. Okay, don't mind yet the operating lines that I have drawn. Just look at the curve that is the result of plotting those data points or those pair of data. So the equilibrium curve that I mean, class, is this one, the black one, which you can see my handwriting for the number of stages. So this is the equilibrium curve for heptane and ethylbenzene system. Okay? Now, let's say, for example, you have plotted it already like this. All you have to do is draw a 45-degree line connecting the two endpoints of this curve. Okay? Now, you draw this particular 45-degree line. Now, after that, then you're ready to determine the things that you need to determine first before you can even plot or draw the operating lines on this equilibrium diagram that you have made. Now, the next thing that we do is, of course, we write down all the given information. So I have you already a screenshot of the solution of this problem for you to easily follow through. This will be an added attachment already in your notes in Canvas, okay, for this particular sample problem. Let me share it to you. So let's say you're doing it, you're drawing your distilling column here. This is your condenser, this is your reboiler, this is your feed. So concerning your feed, you write that its molar flow rate is 200 mole per hour. It's very important that you take note that it is liquid at its boiling point, so meaning it's saturated liquid, having 42 mole percent A and 58 mole percent B. Our A here is heptane and our B here is ethylbenzene. So you have here the reflux liquid. Actually, it's supposed to be L sub O. This is your distillate. And in here, you have your V sub N plus 1 for your vapor that is from your reboiler, which turned into vapor part of the collected liquid here at the bottom. The rest is withdrawn as the bottom's liquid. So it's reflected here. Let me increase the size with class. You could see here that the distillate is 97% heptane and our bottom's liquid is 1.1% heptane by mole. This is our reflux ratio, which is 2.5. So in terms of the requirement in the problem, so you are required for the distillate, the bottom's liquid, the theoretical number of plates, and the feed tray number, or where is your feed plate located. Whenever you start a problem in distillation, of course, you start with the overall material balance. Excuse me. So your feed is equated to the sum of the bottom's liquid and the distillate. We place in the values that we have already in the given. So your feed is 200. The two are unknown. Then from the overall material balance, you make your component material balance, and you multiply this stream speed, bottom's liquid, and distillate with their corresponding mole fraction or mole percentages. So we do that in here, and we replace either the distillate or the bottom's liquid by its equivalent expression of the other. That way you only have one unknown left in here. So from equation 1, we get to see that the distillate is 200 minus the bottom's liquid. So in here, you get to answer right away. Your bottom's liquid and your distillate is 85.3 mole per hour. So in doing the material balance, you get to answer both the bottom's liquid and the distillate. Okay? The next thing that we do in here, in my case, I made use of the slope. That way I can illustrate to you how to use the slope because it's easier. Actually, most of my students would go with the use of the y-intercept. In here, I made use of the slope of the enriching section operating line. I need it, that way I can draw properly my enriching section operating line. So based on the formula that we have discussed and reviewed a while ago, shown to you, the slope of the enriching section operating line is the reflux ratio divided by 1 plus the same reflux ratio. So we substitute our R here and we get this slope. Now, since you already know the slope of your enriching section operating line, in your formula, you have there the XD. So this is the XD, the mole fraction of your A in the distillate. So this is XD and this is XD. You have actually the choice on whatever you will fix first. It's either you fix the X first and solve for the Y, or fix the Y and solve for the X. In my case in here, I assigned a value of the Y, which is 0.7, because I want in my drawing later on that that's how tall or that's how high would be my enriching section operating line, in the manner that it should be reflected in my equilibrium curve. If you want to set the X first, it's fine. So in here, for a Y which is 0.7, I determine the X. So now I have another point. Using the slope, I have another point in my enriching section operating line. So using these coordinates of this point on my enriching section operating line, I was able to draw it. So if I go back to the illustration that was shown to you a while ago, for a Y which is 0.7, this is the Y that which is equal to 0.7, I determine the X. So this is where this is my XD is 0.97. This is 0.9, 0.97, somewhere here. Right, this is my XD. And I connected it to the point which has the coordinate, 0.7. So I have here the 0.7. This is the 0.7 part in here. And the X that I was able to solve, it's 0.532 if I'm not mistaken. So it's 0.5 here, 0.532 somewhere here. Okay, so I've connected the point XD here to that point which I got through the use of the slope of the enriching section operating line to be able to draw this line here. If you notice, there's no problem in plotting the Q line or the feed line because it's saturated liquid. So I need only the mole fraction of the feed, which is 42% mole percent. So that's in here. I just projected it here up and draw a vertical line. Okay, because it's saturated liquid. So where I just made sure that I will have to extend the enriching section operating line in such a way that it will have an intersection on this vertical feed line of mine. Where they intersect, I will connect the exact W here, very, very small because it's just 1.1 mole percent to this point where they intersected. This is now where the three operating lines will meet. The enriching section operating line, the stripping section operating line, and the feed line. And from in here, so since this is the intersection, you see there is this extension here of my stripping section operating line. This is the extension of my enriching section operating line. It need not be like that. It depends on you because anyway, when we do our steps does not depend on the extended part of these operating lines. So it depends on the intersection of the three here. So you just start with XD here on top. Let me enlarge. Hindi na siya ma-enlarge, guys. So if you start here on XD, you go to the equilibrium curve, you stop on the enriching section operating line. That's stage 1, then stage 2, then stage 3, 4, 5, 6, 7, 8, 9, and you have around here 10. So it's very hard to approximate it. So it's just the best approximation of the students that I'm looking for. I'm more after on the construction of these operating lines that they have made. So whatever is the approximation of the student here, let's say for example, it's 9.70 or 9.80, you need to subtract 1 from that to determine the theoretical number of stages because as explained to you, the last stage here is your deboiler. So that's how you determine the number of stages graphically, plotting the enriching section and the stripping section operating lines with your feed line. Okay, so for this problem, that's it. I'd like to go back on the computation. So if you go back there, the number of stages I placed there is 11, so minus 1, so you have 10 plates. The feed plate is on number 6. So let's see. The feed plate location, this is the intersection class. I'll just make it bigger. Some of my students will answer this one 5. It actually depends on the way you have drawn it, not necessarily dependent on my answer. But your drawing of the equilibrium curve had to be not so crude. That way, more or less, your answer is acceptable. So you have here the intersection of the enriching section operating line and the stripping section operating line. The feed plate is you have here 4, this is 5. So actually, if you're going to look at it, your feed plate here, from where the transition is on the 5th plate. Because in here, you have the enriching section, and on the 5th plate, you already transferred on the stripping section. So it's the 5th plate, not the 6th that I have written there. So it depends really on how well you draw it, on where the transition or where the first transfer from one section to the other occurred in your equilibrium diagram. Okay, now if you use the concept of the, what you call this, the y-intercept, that could be one thing that you could use also. Instead of the use of the slope here, you can use the y-intercept. So you use the equation xd over r plus 1. Now, when you got that particular y-intercept, if you have this diagram here, what you're going to do, you just place it in here, the corresponding y-intercept that you have drawn. Connect that point to the point that you have your XD. Of course, you will not extend your enriching section operating line until this particular vertical axis. You will have it within the end point of your enriching section operating line should be within your equilibrium curve. Don't draw until here, but you are actually connecting the XD with the y-intercept determined using the formula XD over R plus 1. So that's the easiest way of plotting your enriching section operating line. Now this problem is easy because it's saturated liquid. If it's not, then you have to use the formula. If it's a cooled liquid or superheated vapor, you use the formula that is suggested by McCabe. If it's saturated vapor, it would be here, but it would be horizontal, somewhere like that, based on the conditions, the special conditions for the Q. Other than that, you really have to determine the Q. If it's a mixture of saturated liquid and saturated vapor, the Q value is the amount of the saturated liquid. Okay, so I think I have overly emphasized that already. So 30% saturated liquid, 70% saturated vapor means that the Q is 0.30. You use the percentage of the saturated liquid part of your feed for your Q if you have a mixture of the two. Okay, let me go back to our slide. I think this is the end of what I prepared for you this afternoon because I want you to read the reading assignments that were assigned to you. And I already updated what you have in your canvas regarding the problem set, the first problem set for distillation. I placed it there already before our class this afternoon. So for the remaining time, you do your reading, and if you have more time, you can process already the problem. There were two problems in the problem set that I have placed. Okay, but do you have any question for now? I will post in Canvas the announcement for the grouping. That way I am updated of what's your grouping. I will paste the announcement there. That way when you submit your second problem set, I know already the grouping. Although you did already the grouping in problem set number 1, I'm not sure if I required you to submit it by group or individually. I have to recheck the instruction that I placed there. But do you have any questions for now as to what we have so far discussed? This particular module has 72 slides, so we're more than half already. We'll finish the other half probably, hopefully next week we'll finish the other half. And speaking of next week, you will have your first quiz here in distillation on Tuesday. Okay, only on the part that I have covered. So that would be on Tuesday, and we will have your continuation of the lecture on this and will be on Thursday afternoon. The 12:30 to 3:30 on Thursday will be allotted again for you to do your problem sets and readings in Canvas as assigned to you. Later, we're going to continue also with this, 5:30 to 6:30. You have any question? I'll stop sharing.